Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available. So we're lucky to host Ray Mooney today. Ray is coming to us from University of Texas, where he has been for 23 years now, graduating the same number of students and having an illustrious career that covered machine learning, natural language processing, data mining. He has a bunch of best paper awards, and he's the president of IMLS. And he comes from Illinois originally, and I know lots of anecdotes about Ray that I would not dare tell here, but feel free to ask me. I will gladly tell them for 6 years of very much enjoying the suffering at Ray's hands at QT. And he'll tell us about some very exciting recent stuff he did in learning and grounding.
Okay, well, thanks for all showing up. I know this is sort of an awkward time. I'm just skipping out on the tutorials at ICML. So I'd like to talk about some of my recent work on learning language from perceptual context. Maybe a number of you know my student David, who was here last summer working with Bill, and just gave, I think both Bill and I agree, quite a nice talk at ACL on that work. He's actually published 2 papers, because he has a workshop paper at the HComp, Human Computation Workshop at AAAI. But this is what he does for a real living. And also my other PhD student, Joo-Yoon Kim, which of course means he's Korean, which is where obviously all my Korean data comes from that you'll see. Okay, so again, hopefully most of this is just blah, blah, blah for people here. So, in NLP, things have really moved towards learning. People tried to build systems manually in the 60s, 70s, 80s, and now almost all NLP systems are constructed by and large using machine learning methods trained on large supervised corpora. From doing syntactic parsing with things like the pin tree bank. I get tired of telling my class about this sentence. To word sense with sense-eval data, and every area has its own little annotated corpora, whether you're doing semantic roles or co-ref or whatever. So the task that I've worked on a lot for actually quite a long time, more than 15 years certainly, is and again this terms of, I think people use it in slightly different ways. I have a particular interpretation, I think, of this term semantic parsing, which is mapping a natural language sentence into what I call here complete, detailed, formal semantic representation, what a linguist might most likely call logical form. Since all our stuff isn't strictly logical, I just use this very generic term, meaning representation, sometimes this sort of not very common acronym MR to mean that. And for a lot of these applications, what I'm interested in is mapping language directly into some computer language that's actually executable. So one of the tasks we looked at starting back in the mid-90s, and I actually saw papers this summer still using this data. It's sort of hopelessly outdated in my mind. Actually, I don't work with it anymore. Answering questions about U.S. geography. I can tell you the story about why we use this data. It's a bit long. So you have questions in English. How many states does the Mississippi run through? Semantic parsing, I want to map that into some very precise logical form. This is like a prologue-y sort of thing. That then I can give to a database and it can answer, which the answer happens to be 10. Another task that we worked on, I have a UT colleague, Peter Stone, who was one of the founders of RoboCup. He got me sucked into the RoboCup vortex, and we'll see more of that later. But this is about the coaching competition. There's actually RoboCup is like 25 tracks. It's like a huge 20-ring circus these days. But they actually have a track called the coaching contest, where you have these simulated players in this very simple 2D simulated soccer world, and you can give them instructions in a very formal language. So we'd like to take an English sentence like this. If the ball is in our penalty area, then all our players except player 4 should stay in our half. In the current RoboCup coach competition, you have to give that in this form. For those who've been around long enough, it looks like Lisp. And it's a very sort of awkward formal language. So we tried to say, well, can't we just map a natural language sentence into that? Then you can actually give that formal expression to the simulator, and the players in the game will actually obey that instruction. So I've done a lot of work over the past 15, 17 years or something on learning semantic parsers. So you want to just give a system a bunch of pairs of natural language paired with logical form, just like I showed, and then it goes into a system and automatically produces a semantic parser. And most of the work I've done, you use no prior knowledge of the language. no parsers, no lexicon, nothing. It has to learn absolutely everything from the NL-MR pairs. And then that you can hopefully give new sentences to, and it will produce useful, correct meaning representations for. So as I said, our first paper on this, which introduced this Geo Query Data, was published with my student John Zelli back in AAAI in '96. And I actively worked on this area through many papers up through an ACL paper a couple of years ago, which this work did actually use an existing syntactic parser, but it's actually the only one of my systems that actually uses any other NLP technology. All the rest of them have to learn everything just from the ML-NR pairs. More recently, other people, as I worked on this for a decade, no one gave a damn about it. But suddenly, recently, there are more people, particularly thanks to Luke Zettelmeyer, which I assume many of you know since he's across the sound, or what do I want to say? He's actually in the et al. On these other papers. He's been the most active. Percy Lang, if you saw his paper at ACL, has been working in the area recently as well. Dan Roth had a student give a talk at the symposium yesterday on it. Also, who else mentioned? Mark Steedman mentioned my work in this area. So suddenly it's actually more popular, which means it's time for me to get out. Actually, a lot of current work doesn't do the standard supervised ML-NR pair, particularly like Dan and Percy's work. Or Ming, who's his new student who gave the talk? Ming Wei. So this is just a little side saying, constructing these annotated corpora, though, particularly for semantic parsing, is very expensive and time-consuming. So I have this sort of catchphrase here. To a large extent, statistical NLP has simply replaced the burden of software engineering with the burden of corpus construction. So what I'd like to do is get a system that can actually learn language more the way a child learns language, by just experiencing it in context. There's a growing amount of work on unsupervised learning, where you just try to learn from raw corpora without any annotation. That's very difficult, and I think all the information you need is not in there. You can do a lot of interesting things with unsupervised language learning with just the text. But, sort of like, the U.S. government wouldn't let you run this experiment, but, try to raise your child and just throw New York Times and web pages and turn the radio on, and they're not going to learn language, right? And I think that's not just because of some human psychological limitation. It's because the information you really need to understand language in any real deep sense isn't in just the signal by itself. It's in its relationship to what's happening in the world when that sentence is being said. So I think the natural way to learn language is to perceive language in the context of its use in the physical and social world. And that requires inferring some notion of the meaning of the sentence from the perceptual context in which that sentence was uttered. So this connects to this general area that I think maybe the best name for is language grounding. That term, as far as I know, was first introduced by Harnad. He published his paper in the Brain and Behavioral Sciences in 1990 called Symbol Grounding, where he argued that the main problem with AI is, you just can't have these empty symbols. They have to somehow be connected to the world, to perception somehow. And, a lot of obvious words are sort of grounded in the perception of the world, like colors and objects like cup and ball and verbs like hit and run. But of course, there's a lot of terms in natural language that are very abstract and don't obviously relate to actual objects and events that you perceive in the world. But even then, a lot of those are actually metaphorical uses of language that originally was grounded, right? We use words like up and down and over and in all sorts of ways, but their initial meaning is a physical meaning. And I think a lot of your understanding and semantics that you attach to those words does come from their original grounded interpretation. Of course, there's a very famous book back from the 70s sometime, I think, right? By Lakoff and Johnson, called Metaphors We Live By, which argues, a lot of language is metaphorically used, and a lot of that metaphor is to things that actually are grounded. So I can say things like, it's difficult to put my ideas into words. I'm treating ideas like objects and words like containers there, and I'm using sort of the semantics of that physically grounded language, but of course, it's a metaphorical use. I think most NLP work represents meaning without any connection to perception, circularly defining meanings of words in terms of other words or meaningless symbols with no firm foundation or grounding in actual perceptual reality. So one little thing I like to look at is look up words in the dictionary and see how circular they are. So you look up sleep in WordNet, it says to be asleep. You look up asleep, it says in a state of sleep. Thank you very much, WordNet. I've learned a lot about sleep. But you and I don't have to be told what sleep is. We do it every night, hopefully, unless you're a grad student. So that's sort of the high-level motivation. So to try to make some concrete progress on that, I'm going to talk today about a couple, I totally admit, very simple sort of toy cases that we've been looking at to try to move in this direction. So the first one I looked at was learning to be a sportscaster. So here I want to learn from realistic data of natural language used in a representative context where I can actually infer the meanings of what may, or at least have a reasonable chance of inferring the meanings of what these sentences are referring to. But I don't want to get boiled down, messed up in all the details of computer perception such as speech and vision. So what we've worked on is learning from textually annotated traces of activity in a simulated environment, in particular taking this RoboCup simulator game, typing in textual sportscasting sort of commentary, seeing if the system can learn to sportscast with no prior knowledge of the language whatsoever, and just listen to read or process the text that's been given to it, associate with the actual events that are happening in the game. So what we do is we have 4 games in our data set. We train it on 3, test it on a 4th. It has to learn to sportscast that 4th game on its own after just watching 3 games being sportscast. So the overall system, here's the simulator. We have a very simple sort of rule-based system that looks at the detail of the simulator, which basically gives you the position and velocity of all the players and their direction of angle. That little mark is sort of where they look. They do have a cone of vision. It's actually not a bad simulator. It simulates friction and vision and all these sorts of things, but it's a very simple 2D thing. Pulls out a set of perceived facts in a logical form about events that are happening. And that's not influenced by language at all. I assume a lot of us here went to the very nice Whorfian sort of talk at ACL, which I thought was a great talk. So there's no sort of Whorfian stuff going on here because the facts that are perceived are not influenced by language at all. Those are just assumed to come out. Then we have the Sportscaster saying something that goes into a grounded language learner. And one of the semantic parsing systems I built is based on a probabilistic version of synchronous context-free grammars. One of the reasons I like that work, we have a system called WASP. It was the best paper at ACL in Prague. It supports that same representation, both supports language generation and semantic parsing. The language generator has to have a language model in addition. But, so we're interested in the language generation side of things. So we can you play a new game, the so-called simulate perception pulls out a bunch of facts, and then the language generator can generate that into language. Okay? So what I like to do here to give you an idea of what this looks like, do we have any Korean speakers in the audience? Oh boy, a couple. So you are no longer valid subjects for this part of the talk. So my Korean student Ju-yoon was nice enough to comment on this game. So imagine I showed you 3 of these games for the non-Korean speakers, and then I give you a 4th game and you have to sportscast it in Korean. Takes a little while before it starts talking. The text-to-speech is just off the shelf. It generates the text.
보라 3이 보라 8에게 패스합니다. 보라 8이 보라 10에게 패스합니다. 보라 10이 보라 11에게 패스합니다.
Very nice script in Korean, right? Hangul. It's very phonetic because some king who was also a
보라
linguist
11이
designed this
패스한
in like
공이
what the
중간에서 분홍 5에게
1600s or something, I
가로채기
think?
당합니다. 분홍 5가 패스한 공이 보라 10에게 가로채기 당합니다. 보라 10이 보라 11에게 패스합니다.
So think, could you do what my system does, which is learn to sportscast in Korean? After I showed you 3 games of this, you'd be bored to tears, but I don't know if you could do it. So what the system really deals with, again, I don't do speech or vision or anything, it ends up with these set of sentences and then a string of these sort of logical terms. Now, it's not using anything about the orthography of these. So really, it's more like this. It's just a bunch of empty symbols as far as the program's concerned. And because it can learn both English and Korean basically equally well.
And the timestamps or something?
Yeah. So the way this works, is, it takes everything that came out of the perception in the last 5 seconds. When it sees a sentence, it attaches these dotted lines saying, I don't know, but this might mean that. And here I add the green ones, which are ones that we've annotated after the fact to what we think is probably the correct one. Some things don't, right? Because this is pink 11 looks around for a teammate. The perception doesn't extract anything like that. Purple team is very sloppy today. It's actually interesting. There I think you need to do some sort of Whorfian stuff where it would have to learn the concept of sloppy based on. So obviously what's happened there is Purple's turned the ball over several times in a row, so they say they're being sloppy. But perception can't directly extract that. So it's a very noisy signal. On the green lines, of course, we never give to the system. Those are used, purely for evaluation purposes. And again, there's really like a bunch of empty symbols over there. So if we can figure out the green lines from all the dashed lines, then we can just train a supervised semantic parser on it, which is basically what we end up doing. And then I can use, all the history of stuff, or Luke's stuff, or Dan's stuff, or whatever you want once you have it in supervised form. Another problem here that you may not have realized that it has to address is either what natural language generation people either call content selection or strategic generation, which is not only knowing, how to say something, I give you the logical form, generate the language, but what to say. What out of all the various facts that my perceptual system is observing, which ones are actually worth talking about? And so we have to actually also effectively choose. So, the perception pulls out all these sorts of facts. The system all has to learn a model of what's worth talking about. It pulls out these. Our current system is pretty simple. It just focuses on what events seem to be highly mentioned. But of course, I have to learn that from this ambiguous supervision. If I had the green lines, it'd be trivial to calculate probabilities on mentioning each of these things. But it has to learn the green lines and then estimate those probabilities. Okay, so the data that we played with, we collected 4 RoboCup championship games from the actual competition from 2001 to 2004. The event extractor pulls out about 2,600 events in a given game, and these were annotated by my grad. So David, those met him last summer. He did the English. I should get him to do the Mandarin Chinese. I have all these Chinese students. They've never given me a Chinese corpus. I got to fix that. And then Juyun commented the games in Korea, and they both used about pretty much the same number of sentences. Each sentence is matched to all events within the previous 5 seconds, which gives you a relatively small but at least some level of ambiguity. That means on average, there's 2.5 events associated with each sentence, but it's a bit of a variance from 1 up to 12. And then we manually annotated those with the correct matching, those green lines, but that's not used by the program. It's only used in evaluation. Algorithm, I'm not going to talk. Yeah, sure.
The correct matching is always to just a single event, or does it sometimes multiple events?
Yeah, so that's a good question, and we've assumed here just a single match. So it's 1-to-1. And so, sometimes it's not matched at all, but if it is matched, it's matched to one thing. There are other cases where obviously that assumption won't work. It could either be many-to-1 or one-to-many. We haven't specifically looked at that. So here, it worked pretty well for this case, but I do believe it's a limitation. So we use a sort of EM iterative retraining sort of process to resolve those ambiguities. And then it calls a supervised semantic parser learning. You can use whatever system you want to do the supervised learning. And basically it goes in a loop like this. First of all, it just assumes all those dotted lines are actually real annotations. So it's very noisy, right? Because it's 2.5. So most of that, 3/4 of it or something, right, is garbage. But it learns something from that, and then it goes into an iterative loop. Again, it's very EM-like. You train the supervised parser on the current, usually quite noisy examples to start with. Use the current trained parser to pick the best MR for each NL. So it's really what someone usually calls hard EM. You don't associate. We'd actually tried something more where we actually keep the uncertainty as you go through the loop. It actually did worse. I'm interested in, people heard the term hard EM before. Other people have tried it, where you actually just pick the best answer at each point. You don't put the probability distribution on it. Then you create new training examples based on those assignments, and then you iterate. And hopefully each time through it gets better. I don't have any convergence proofs because this isn't a real generative model. But in practice, 3-4 iterations, in practice it converges. If you're interested in more details, there's a lot of details in this journal paper we wrote a little over a year ago that appeared in JAIR, the online journal for artificial intelligence research. Okay, so this isn't a very algorithm-heavy talk. So here's the English demo. We tried different approaches. I'm not talking about the details. There's a lot of different variations of the basic algorithm that we tried. You can read the paper for details. These are the ones from the best performing thing that we built. Again, the speech is just synthesized, using this system from CMU, free TTS, text-to-speech. And it outputs the text, and then the speech synthesizer. It's so much easier to watch these things when you actually get the speech, rather than trying to read. It's like trying to watch a soccer game while you're reading subtitles. It's not very easy or fun. So this is on the test game, right? It has never seen this game before. It's trained on 3 games in English, and now it knows how to sportscast. Sort of slow down so you can follow it.
Purple 5 passes to purple 11.
Again, it has to learn the names of all the players, the syntax of the language, everything. Just, there's no built-in knowledge of language whatsoever. It has to learn all of that from scratch.
Purple 11 passes to purple 6. Purple 6 passes to purple 11. Purple 11 passes to purple 6.
A little bit like
purple 6 passes to purple 8. Purple 8 passes to purple 11. Purple 11 makes a bad pass that was intercepted by pink 6. Pink 6 passes back to pink 7. Pink 7 passes to pink 9.
I guess we'll
pink 9 passes to pink 11. Pink 11 passes to pink 9. Team is offside.
Okay. So the paper presents all sorts of evaluations of this. We looked at a lot of different factors about how well it's learning, how well can it figure out those green lines from the dashed lines, how well it can match sentences to the correct meanings, how well does the semantic parser work trained on the supervised data that results from that, parsing sentences into formal meanings, how well does it generate sentences from those formal meanings, and how well does it solve the content selection problem of picking which events are worth talking about. There's all sorts of numbers on that if you're interested in there, but I won't bore you with the details. The one experimental and my favorite evaluation that we did is what I've called the pseudo Turing test. Of course, you got to use Amazon Mechanical Turk to do all the work these days. So we recruited human judges, 36 in English. It's harder to get Korean speakers. But I think Julian just called up his friends in Korea and said, hey, check out this thing on Amazon Turk. We had 8 commented game clips, 4-minute clips randomly selected from each of the 4 games. Each clip was commented once by the human and then once by the machine, of course, when that was left out as a test game. The judges were not told which ones were human or machine, but we did tell them half of them are generated by a machine, half of them by a human. Then we asked them basically 4 questions. We had them rate on a 5-point scale, the English fluency from flawless to gibberish, semantic correctness, where we tried to explain to the Turkers what we meant by this was, is it really saying something that actually happened in the game, from always to never. And then this very vague question was just like, how good a sportscaster is this? The scores on that were actually all low because it's very boring. From excellent to terrible. And we also, again, told them half of them are human, half are not. And it says, you have to guess which ones of these were generated by a human being. So here's a breakdown across all the games. Here's the averages for the English case at the bottom. You see, the ratings of machine here are actually higher here, about the same, a little higher there. And, most humans and machines are not human, only about 25%. But actually more of the machines were human than the humans were human. But this is partly, if you look at the game-by-game results, this is partly, notice this huge discrepancy on the 2004 game. And that was because apparently it randomly assigned some representation to an interesting sentence in the corpus, like this is the beginning of an exciting match in 2004, or something like this. And the system just happened to spit that out for this game, and it got lucky. It didn't do it for any good reason, and that sounded to them much more human, and so it won decisively on that game. Now, another thing is I should have realized that David wasn't such much of a soccer fan, and Juyun was, so his games are actually commented much more interestingly. So we didn't actually. So 62% of the Amazon Turkers actually believe that Juyun was human, and only 30% believe that our learned sportscaster was human. But it's just filled a third of the people. Again, the scores are, correspondingly are a little bit worse. But basically, you can listen to these things, you can follow them. They actually, it works basically, and there's more numbers in the paper if you're interested. Okay, so we stopped working on this a couple of years ago now, and went and put the paper together and published it. So a new problem that David's been working on for the last couple of years, and we finally got some halfway decent results for it. It's a paper at AAAI. I also gave a poster. Was anyone at my poster yesterday? No, at the symposium yesterday. And this is learning to follow directions in a virtual world. So the idea is learn to interpret navigation instructions in a virtual environment by simply observing humans given and following such directions. Again, no prior knowledge of the language. We've only done this in English so far. But you just watch people give directions to another person in a virtual environment, and that's all you get to see. And you have to now learn the language and learn to accept directions yourself. And I think even within the virtual world, I think there are potentially interesting applications for this, where you can build virtual agents in video games and grow them, raise them like a baby, and teach them language and then interact with them. So it's like you could have Sims where you can actually raise your baby and teach it to talk and then have a conversation rather than just mute Sims. And hopefully there could be some interesting applications for that. So what we did was another student at UT who was actually interested, he worked with Ben Kuipers, he was interested in building a wheelchair that could follow directions in natural language for severely impaired people. But to do experiments for his thesis, he built this little virtual environment where these colors here are the tile on the bottom of the floor. It's just a bunch of connected hallways. Then there's different wallpaper on the walls in each of the hallways, which is based on what these pictures are. I don't know why I came up with these things. And then there are objects scattered around in the environment: hat rack, lamp, easel, sofa, bar stool, and chair. So this is what it looks like to the actual people who are doing the task. They're in the, this is the bird's eye view, but this is what they see. And the humans, they had to actually explore this environment from this perspective and then learn it. And then they were asked, give instructions to get from this place to that place to another human, and then another human followed those directions to see if they could get there. So here's an example starting here, ending there. People generate very different descriptions using different types of strategies to generate these directions. So these are all 4 different directions for the exactly same task. And you can see there's quite a bit of variation there. Take the first left, go all the way down until you hit a dead end, go towards a coat hanger and turn left, go straight down the hallway, etc. They don't actually know what an octagon is because, of course, that is a hexagon. So it has to learn, we got dumb teachers, so it actually learns that octagons are hexagons, I guess. Okay, so this is the path that they all take, but there are 4 different ways that various humans came up with to describe that path. All we see is the text and the primitive actions that get performed: forward, left, forward, forward. And you have to learn to map those complicated English instructions, given all the information about the environment. The system also knows the whole environment, has a symbolic representation of all the things in the environment. But it has to now learn to accept directions and produce primitive actions just by watching other people follow directions. So I have a little demo and an app. So this is the little cone here is like a vision cone for the agent as it's following this direction. So it'll put each, place your back against the wall, the T-junction, turn left. The graphics are pretty poor for reasons I don't want to go through. Go forward, the intersection contains a hat rack, turn left. Go forward 3 segments to an intersection with a bare concrete wall passing a lamp. So you really hardly see the lamp, I think. So this is what the system experiences, and it has to now learn to follow directions in natural language based on just that experience with no prior knowledge of the language. Okay. So again, there are many different instructions for the same task. They describe different actions, they use different landmarks, and they talk about the landmarks in different ways. And the meaning representations are completely hidden from the system, right? It just sees the primitive actions. It doesn't see the plan that the system would actually need to execute those actions and figure out that's what they need to do. So unlike the sportscasting, where each sentence, by looking at this 5-second window, contains a fixed number of options, there's actually a combinatorial number because there's a lot of stuff in the world. And the person could be referring to basically any subset of that. So you get a combinatorial explosion in the number of possible plans for describing the same sequence of primitive actions. So we couldn't take the same sort of EM approach that we took with the sportscasting case because there's just too many possible MRs for each NL, to use my lingo. But at the end of the day, this is what it gets. It gets these triples of, it gets a natural language sentence, it gets an observed sequence of actions that were executed after the person said that sentence, and then it knows the state of the world, all the objects and the wallpaper and the tile in each of those states. And so you get these triples of language, action, world state, and that's what it gets, and then it has to build a correct mapping from actions from the natural language into the actions, given, of course, the knowledge of the world state. Okay? So the overall system we built looks a little bit like this. So it first looks at the world state and the trace of actions that were executed and constructs various ways of sort of coming up with a possible plan for that. And we'll look at those in a minute. But then it goes through what we call a plan refinement step, because these usually contain too much information. It was as if everyone told you everything you saw at every point. And that's not true, of course. So we do what we call plan refinement. It actually looks at the language. It learns a lexicon about what it thinks the words mean. So the first one to do this sort of stuff was Jeff Siskin, if you know his work, and I had a student, Cindy Thompson, that did sort of things like this too, to sort of learn pieces of representation that seems to correlate with words. Then it uses those meanings of words to sort of pull out the garbage from the plan and just pare it down to what it thinks the language is actually talking about. Then it gets pairs of the instructions with the inferred plan for that, given lexical knowledge that it's learned, and then it just trains a supervised semantic parser on those pairs. Now, of course, in testing, you get an instruction. The semantic parser maps it into a formal representation. That then goes to an execution module. Marco was this system that could execute those formal plan representations that Matt McMahon built as part of his thesis. And of course, it knows the world state, and then it produces an action. So a little bit about those two things. So we sort of bound the representation of a plan by two things. One is you just mentioned the primitive actions. The other, after every action, you put in everything in the world that you observe at that point. So you turn left, then you verify that there's a wall to the left, a lamp to the back, a hat rack to the back, and a brick wall in front of you. And it's actually not even all here because it doesn't have the tile, but that would be there too. And then you take a step and you verify that you're in the wood hall. And so this is very detailed, much more than what the language is actually talking about. So we need to figure out how to pare this down into what we think the language is actually referring to. So we need to remove those extraneous details in the landmark plans. And we do that by learning the lexicon and then remove the parts that don't seem to correspond to words that actually appear in the sentence. So let's go to the example here. So here's two cases. Again, this is a simplified form to fit on a slide. So the real landmark plans are much more, but somewhat more complicated than this. So this is turn and walk to the sofa. And another case is walk to the sofa and turn left. So it takes all the sequences of actions it saw in every sentence where the person mentions sofa, say. I really should change this to like couch, because it's not using the fact that this sofa means that, because it could be in Korean or Spanish or something else. And we take an intersection of these two graphs, because they both use the word sofa. So presumably, again, the word could be ambiguous, but in general, it's not a bad heuristic that probably sofa means something that's shared by these two examples. But there's sort of multiple things it could be. It could mean turn left and until you see the blue hallway, or it could mean travel and see if you're at the sofa, because those are two maximal subgraphs shared by these two plans. So what it does is the lexicon learning looks a little bit like this. It collects all the landmark plans that co-occurred with a particular word and says, well, maybe those little pieces of graphs are things that word refers to. And it keeps doing that, adding new entries. And then it ranks the final set of candidates by this simple score, which says you want to find a piece of graph that's very likely given the word, but not so likely when the word's not there. And so then it learns this sort of ranked lexicon, pieces of graph as the, quote, meaning of each of the words. And once it has that, it then tries to simplify the plan by just looking at the word. So here it says, well, I think turn left means this, so pull that out. I think walk to the sofa means that, so pull that out. And then and is the only thing it left that doesn't have any meanings in the lexicon that it learned. And then it reduces that more complicated plan to this subpiece, which it thinks is composed of pieces that correspond to the meanings of the words that actually appeared in the sentence. So there's a little bit of pseudocode here in the earlier slide about, it selects the highest scoring entry at each point in the lexicon, removes that word from the sentence, and then keeps doing that until it's exhausted the words in the sentence. Okay, so hopefully that gives you a little bit of idea of how it pares down the whole big plan to what the subplan is that it thinks the person is actually talking about. So again, if you're interested, the AAAI paper is already up on our website if you want to read some more of the details. A little bit of thing on the data. Again, we didn't collect this data. Matt McMahon, a previous student, which I think, Misha, you said you knew Matt, right? He collected instructions from 1 to 15 followers. I'm sorry, with 6 instructors, 1 to 15 followers, 3 different maps. So they all have the same types of tile and objects, but they're all arranged differently in each of those 3. And we do leave one map out cross-validation, which means we train on 2 environments. And we want to see, of course, whether it can generalize to follow instructions in a new environment. Same sort of primitive objects and things in the world, but they're all arranged differently. So there's a few statistics. You can look at the entire instruction for a paragraph, or you can look at the individual sentences for it. These are various statistics. There are about 700 instructions with 660 words. The single sentences, of course, are a little bit less. So the entire instruction usually takes, you need to do like 10 actions to follow the entire paragraph of instructions for how to get to the goal. We did a number of different evaluations. Again, I'd point you to the paper for some of these. I'll just present results for what I call the end-to-end execution, where you train it on 3 maps. It gets to watch the instructions followed in those 3 maps. You give it a new map. You give it an instruction. You say, go. You see if it follows it correctly and gets to the right place. Again, we did leave one map out cross-validation. It's a pretty strict metric. Only if the correct final position exactly matches the goal do you get a point for that problem. But we looked at it both at the sentence level. After each sentence, do you end up in the right place you should be? And then after the entire paragraph for that whole instruction, do you end up in the right place? We built what I think is a reasonable sort of lower baseline to sort of give you an idea how hard the problem is. We built a very simple probabilistic generative model of the actions in the plan. So actions that are more likely to come out of this generative model. And then you sort of execute that generative model. So it doesn't look at the language at all. It just says, oh, do actions in sort of a very simple generative model of how the plans actually occurred in practice. We thought that was a pretty good lower baseline. Upper baselines, we did, what if we manually annotate sentences in this domain with their actual correct plan representation? Matt built the system totally by hand, no learning involved, but also he hand engineered the system for all 4 of these, 3 or 4, how many maps are 3, I think. So it's really like testing on the training data. So his scores will seem high, but take into account that that's basically testing on training data, development data. Matt didn't do a good job of separating development from test. And of course, how well do humans do when they follow these directions? So a bunch of numbers here. So first is, how accurately can it follow a single sentence? The simple generative model, the lower baseline is about 11% of the time it'll actually do the right thing. If we train a system on those basic plans that just have the primitive actions, at a single sentence level, it actually doesn't do that bad. It gets about 56%. If we train it on the landmark plan, it has too much. So this is like something I call these Goldilocks. This is being trained on too little of a representation for the meaning. This is being trained on too much of a representation for the meaning. And they both, so this actually does pretty well. This does quite a bit worse. If we put in our lexicon learner and refine the plans before we produce the gold standard that goes into the training of the supervised parser, then we actually don't even do as well as the basic plans for a single sentence, which is a little bit disappointing. If you train the system on human annotated plans, so this is giving the supervised parser gold standard annotated data, it only gets about 58%. Marco, because it was sort of overfit to this data, is about 77, and the human followers were never judged on their ability to follow a single sentence. If you go to the complete plan, of course, everything gets quite a bit worse, because if you misparse any of the sentences in the instruction, you're going to screw up and you're not going to get to the right place. So, this shows you that the simple generative model just gets 2%. So the chance that you're going to just sort of mimic the type of actions that were performed during training and get it right is very low. If you train on basic plans. So here's really our, the best result for our systems. Not that great, but 16% of the time, it can actually follow the entire directions and get to the right place. And notice here, it actually is doing better than the basic plans, because those verify steps, they actually, because the executor can actually correct some errors, because if it says, you should see the hat rack, and you go one step, you should see the hat rack, and you see the hat rack the next thing, it'll actually go ahead and go to the hat rack. So it can sort of fix errors in the instructions themselves by using those verification steps. If you train on human annotated plans, it gets about 26%. Marco, again, overfit to this data 55, and then human followers only get 70% of the time are they able to, because sometimes there's errors, and these are real plans that people generate, sometimes they're just wrong. And so human followers only get about 70% correct destination in this environment. Here's just a sample parse where the system actually learned to parse this pretty complicated instruction completely correct. This plan will actually get you to the right destination. Place your back against the wall of the T intersection. Turn left. Go forward along the pink-flowered carpet hall, 2 segments to the intersection with the brick wall. I wonder what the parse it got for that. It's in here somewhere. This intersection contains a hat rack. Turn left. Go forward 3 segments to an intersection with a bare concrete wall, passing a lamp. That's your goal. And it actually got a plan out of that. Again, it didn't understand everything right. Notice what it picked up brick hallway. What didn't it get here? Pink flowered carpet, it didn't even get that. But this is sort of overly, people do this redundantly. There's more information here than you need. So the fact that it doesn't pick up all the information is okay. It's still good enough to work. Okay, so that's the quick tour of these 2 applications we've looked at to try to judge grounded language learning, where again the system starts with no knowledge of the language, has to learn everything about the language just by watching things, either watching a game being sportscast in a RoboCup simulator, or watching 2 people, one giving instructions to another and them executing a sequence of actions. The current systems are both very passive. They just sit there and watch. They're not, hopefully your child isn't like this when he or she is learning language. They're interacting and other things. So we'd like to move to a more interactive, active form of learning here, where either the system itself sort of tries to, the interactive learner acts as a follower, so it actually participates in the process and tries to follow the directions and sort of has a more interaction with the world rather than just passively observing 2 people doing it, or acting as an instructor. It tries to generate things, see what people do, learns more from sort of generating the language and seeing people's response to it. And of course, it would want to generate good things, things that it's uncertain about. There's a lot of sort of active learning ideas that could go into this. And this would even make it more, I think, like, maybe a little bit more how people learn language rather than just passively observing the world. More generally, I'm interested in sort of language grounding in general. I've done a little bit of work not in simulated, so both of these are just in simulated world, because I'm not a robotics or a computer vision person. But I am interested in this general area of integrating language and vision. There was a workshop at NSF held about a month ago that I went to where they threw together half computational linguists and half vision people, and we yelled at each other for a day. The thing is there's actually an interlingua. I don't understand vision people. They don't understand language people. But we actually have an interlingua. It's called machine learning. All they do is machine learning. All language people do is machine learning. So you just talk in SVMs and kernels and graphical models and EM, and it's like you can actually talk to these guys. But of course, generally, they all have to do supervised learning. So they have Turkers. They actually have better. They can get Turkers to do more fun tasks because they have them, identify objects and images and outline them. And it's like they have an easier job getting Turkers to do what they want them to do than language people get them to do what we want them to do. But that's still, Turkey has made it cheaper, but it's still, costly. It'd be nice if we didn't have to do that. So sort of part of my vision is can't we do cross-supervision of language and vision? Use naturally occurring perceptual inputs to supervise language learning and use naturally occurring linguistic input to supervise visual learning. So we got to go back to the 60s at MIT and do the blocks world where we have this. And I give it a sentence. The blue cylinder is on top of a red cube. If I'm trying to learn language, I view this as my input that I want to understand, and this is my supervision that I'm going to use to train that. If I'm doing vision, then I treat this as my input, and I treat my language as my supervision. So they each sort of supervise each other, and I can learn both vision and language by the correspondence between vision and language. So again, this is just a high-level sort of vision, about vision or something. I've done a little bit of work with real video and real images, but again, I'm learning a little bit more about vision, but I'm certainly not at all. I have a hard enough time keeping up with both machine learning and natural language, much less getting into vision or robotics. My students love me, right? Because now I say, okay, if you want to work with me on ground language, you have to take the computer vision class, the robotics class, the learning class, and the language class. And if they survive that, then it's like, okay, you can work with me on grounded language. So we've done a little bit of work with closed caption video, where you use the closed captions as a very weak sort of supervision to do what vision people call activity recognition. So we've automatically trained activity recognizers to be used to improve the precision of video retrieval. So of course we did this in soccer. So that was a nice thing. This allowed me to use my grant money to buy a TiVo machine, because that's the best way to get the closed caption text from the video. Because YouTube, they don't give you a closed caption text with them. And we tried to learn activity recognizers for 4 different verbs: kick, save, touch, something else. I'm not a soccer person. I don't play video games, and I hate sports, and somehow I'm doing video games and sports. I don't know how that happened. But it just uses the fact that these words, and most of this is noise, because most of the time when the caption says kick, no one's actually kicking in the image, but there's some probability. So you can actually use this as a very weak supervisory signal and learn an activity recognizer that's really bad, but if you add it on top of the text, it actually improves the precision of your image retrieval, your video clip retrieval.
So
This is a AAAI paper last year. If people are more interested.
Now respect the language, just in terms of recognition of actions and videos. What's the
We used off-the-shelf stuff. This is stuff by Loptev. Huh?
Is the state of the art at all decent?
For these sorts of, if you have, John, someone taping their graduate students say walking, waving, then it works pretty well. If you run it on real video, it's pretty crappy. Yeah, it's pretty crappy. But the point is, you can do the retrieval of events just by looking at the words. And then we filter that through the activity recognizer. So the activity recognizer is just acting as a filter on the language retrieval. And we just show that you can, and the numbers are in the paper, you can improve the F measure and map scores and these things for your video retrieval by adding the activity recognizer that you learn from this crappy signal on top of the linguistic-based retrieval. Again, that's a AAAI paper last year if you're interested. So one thing I learned from this whole thing is, don't write your good master's students too good of recommendation letters, because then they get into Stanford and they leave. Sonal's now working with Christina's old advisor, Chris Manning. So I have to write crappier letters in the future. So current language, so I'm wrapping up here. So current language learning approaches use expensive, unrealistic training data, blah, blah, blah. So we've been trying to focus on this idea of learning language from systems with sentences paired with actual environments that the language refers to. Right now we've explored a couple of admittedly simple but I think interesting challenge problems. Learning to sportscast simulated RoboCup games, where we're actually able to commentate games about as well as humans. And learning to follow navigation instructions, turns out that's much harder, but we're able to accurately follow individual sentences at about the 55% level, complete instructions, as you saw, not too great, 15, 16%. But I think this whole area of grounded language learning is starting to take off a little bit more. Regina Barzlay's been doing things. Luke Zettelmeyer's been doing things. I've contaminated them with some of these ideas. And I hope more of you get interested in these things, because I think this is the future. Okay, that's just backup.
From the TiVo, you
Yeah.
just had someone.
Yeah, it took Sonal a while to figure that out, but yeah. But yeah, like I said, I had to write like a special letter. Yes, I'm actually buying the TiVo machine to do research.
So is there just arbitrary amounts of that sort of data available? So even if signals
We recorded it off, cable TV or whatever. That's why we got the TiVo box. So I don't know. I mean, we didn't do a deep look at this, but I don't think you can find much closed caption video online, as far as I know, easily. I mean, there's a bunch of it out there, right? But it's broadcast and it's not on YouTube, right? So getting that data is a bit tricky unless you buy the TiVo machine and record it live off the TV yourself. But this is actually an idea. When I first heard of closed caption in the early 90s or something, I said, wow, I'd like to do language learning on that. And it's just taken me 20 years to do something.
For the sportscasting application, there are video games out there. Like I'm kind
Sure.
of with you, sports and video games are not my forte, but I've seen them and they commentate on all the stupid.
Sure, so it's all handwritten, right?
So it's all handwritten.
So if you want to, well, estimate with 99% probability. Those are all hand-engineered systems, right? My system starts with no knowledge of the language, no knowledge of anything. It has to learn it all from scratch, right? So I care more about you can hand build. There's actually RoboCup sportscasters that were hand built, and they're actually pretty good. But, they're hand built. You put in the patterns, because it's a pretty simple text generation problem. You just do template-based generation. But the point of this is not, in some sense, the sophistication of the language that it gets. It's that it's learning it from this very weak signal.
What about these live gaming systems? So I know there are setups where you can play multiplayer gaming systems and you have like a mic and headset, like a closed talk microphone, or you can like text and comment.
Wow, yeah, we need data to collect it. I'd also need a good speech recognizer person, which I don't have. But yeah, if we could do the speech there, well, with those mic things, it's much better speech recognition if you have the
of course,
voice.
they're probably going to be cursing and saying all
Yeah, well, that'd be a good generator. You have to put a profanity filter, pound sign, backslash, bang, bang.
But it's actually, in the real color commentary, a lot of it is not very structured with respect to the video.
So if you look at sometimes I call this sportscasting for Sesame Street, or maybe for Teletubbies, or what's even lower than that, I don't know. Because, it's very literal. What we put in is very literal. You watch real sportscasts, because they're assuming you can watch the game, right? So what I'd like to get a hold of is what's called SAP. I don't know if people know about SAP, Secondary Audio Program. Because there but I now have to do the speech problem, because I knocked my TV into one of these like in the mid-90s too. I'm watching some PBS nature show, and there's this other voice coming, and now the lion approaches the cub. And I'm like, what the hell happened? And I flipped it into SAP. And that is the sort of signal I want. The other thing people have done is looked at scripts typed in by fanatic fans, right? So there's this famous paper in Vision using Buffy the Vampire Slayer, where every episode of Buffy has been meticulously hand-coded into very detailed strips about every action and every dialogue piece in the entire series. And you can get this data online, and people have tried to align that to the video, and you can use that sort of thing as training. But now you're just exploiting a lot of human training there, based on very detailed human annotation. So I think there are other sorts of interesting signals connecting language to video. Normal closed caption is actually pretty bad, because it actually rarely is talking about what actually is happening on the screen.
You could look at tweets right after.
So there are these sites that post an online I've talked to this about my students, the online commentary on the game on the internet while it's being played. That's an interesting source that we've considered. Another thing we consider, actually, Percy's looking at this thing of cooking shows, but he's doing it in the virtual environment. So he has this. I just asked him about this last week in Portland, but he's never gotten anything working on this. But he told me about this last year, and I thought it was a cool thing. He built a virtual kitchen, and he just gives people recipes, and they have to cook things in the virtual kitchen, and then he wants a system that can be a virtual cook, follow new recipes. But he doesn't actually got anything. Apparently, he set all this up, and then he got off. Percy's doing like 10 different things at once or something. Yeah. So
I love the idea of grounded language, but it feels like we're suffering from a lack of data. So subtitles are one way to get at it. Is there some, I don't know, do you have great ideas about how we can port into new domains, how we can get people to provide us with that?
So I sort of like the virtual environment. If we could actually build sims with language and get people to talk to it. So I think if we built interesting virtual languages where you could actually talk about things in that virtual language and get people at least patient enough to it takes a long time to raise a baby to learn to talk. I just met Misha's kid. She's almost 1.5. She doesn't say a single word. It's not an easy problem, right?
Plotting performance on that navigation task against age. You have about 100 one-year-olds do it, 2-year-olds, 3-year-olds.
So people, raising a baby in the real world is tough. Raising it in the virtual world and giving it enough linguistic experience to actually learn the language, I don't know if people would be willing to do that, because it probably require a lot of data.
But Misha isn't learning a different brain for RoboCup games versus a brain for following directions, right? Is there some way that we can leverage data from across domains somehow? Or, is there some generalization capability that might allow us to do more with less data or something?
I'm open to
if you want sports data, I think in India they still have, and probably other countries, actual radio broadcasts, right? So that will be much more limited.
Yeah,
right?
I thought about that.
The radio commentary of a cricket match actually tells you exactly what's going on, because it's not assuming that you have...
Now, my dad used to always listen to baseball games on the radio when I was a kid.
And presumably you can get the video feed as well. Now you'd have a synchronization problem.
Nope, that's a good idea. I've thought about that too.
In a shortwave radio.
I was just saying, along the same lines, football coaches like have right after the game, they will go through like the most literal like analyzations, and that's taking it slowing down and really.
You have to do the alignment.
Yeah, but that's I think more distilled than a sportscaster who's trying to keep an audience.
Yeah. Yeah, so I think there are a lot of possibilities, and we've only barely scratched the surface. And I think there are other sources of data. Are they any of them perfect? Certainly not.
When you do EM training, how do you learn? Like, what features are you using in order to learn the best meaning representation?
So again, at the end of the day, it's just training a supervised semantic parser. So different systems use different sets of features. So I would point you. So what we used with the RoboCup is a system called Lambda WASP. It was the Prague ACL Best Paper Award. It learns this synchronous context-free grammar rules to do the mapping. But that to me is a separate problem. I worked on that for 16 years. Now other people are working on it finally. So there are a number of systems out there. Our code is available online. It's not documented or supported, but you can download it. I think a few people have actually got it working. Okay, thank you.